In this program, we're going to look at the differentiability of a function from r squared the plane to r the real line. And our definition is a generalization of the familiar definition for a function from r to r. We'll look at this in the second part of the program. But to begin with, there's another way to approach the concept. You see, we actually know how to differentiate functions from r to r. So let's make use of that. Now, it's not too difficult to construct some functions from r to r from any given function from r squared to r. Well, let's look at a particular example. It's quite an easy one to remember. It's the function that maps the point xy to the number x squared plus y squared. Now, we know that such a function can be represented by a surface. And here it is. It's just a paraboloid. Now we're going to look at the point 1, 2 in its domain. Well, the function maps this point to a point on the surface, a vertical distance 1 squared plus 2 squared, or 5 units above the xy plane. Now there's a quick way of getting an r to r function, and that is to slice this surface by a vertical plane through this point.
So here's our general slice, and if I turn the model round like this and remove this part, what we can see is the cross-section. It's a parabola, and we're going to think of it as the graph of a function from r to r. Well, later on we're going to find the form of this function for this general slice, but first of all we're going to look at slices in more obvious directions. In fact, we're going to look at slices parallel to the axes. Well, let's first look at this slice, parallel to the x-axis. Now, since the positive x direction points out here, I'm going to have to remove this and turn it round so that the positive x direction now points to the right. Well, the function I'm interested in is the one whose points are given by this set. They're the points on the surface that were directly above the line y equals 2. And we can find their equation like this. The function f takes the point xy to x squared plus y squared. We're just interested in the image of the points where y equals 2. This gives us a function of x, which we call f1. And it takes x to x squared plus 4. Okay, so here's the graph of the function x squared plus 4. And since we're interested in the behavior of the surface above the point 1, 2, we're interested in the behavior of this graph when x equals 1. And since we're interested in differentiation, we're interested in the slope of the tangent line here. Now, we know that the slope of the tangent is just given by the value of the derivative of this function when x equals 1. And we can easily calculate this value. It's 2. And we call this the value of the first partial derivative at the point 1, 2. And we write it like this, with the 1 next to the d, to remind us that we're differentiating a function of the first variable x. Well, that's dealt with a slice parallel to the x-axis. Now let's try a slice parallel to the y-axis. Well, here it is. I'll just turn it round. And again, the cross-section is a parabola. And again, we're going to think of it as the graph of a function. And we can easily find what the function is, because on this slice, the value of x is fixed at 1. So x squared plus y squared just becomes 1 plus y squared, and we're interested in the function f2 that maps y to 1 plus y squared. Well, again, we're interested in the behavior of the surface here, so we're interested in the behavior of this function when y equals 2. Now, we can differentiate this, and we get 2y, and when we set y equals 2, we get 4, and we call that the value of the second partial derivative. And we write it like this, with our 2 next to the d, to indicate that all along we've been dealing with a function of y, the second variable.
Well, in general, for any function f from r squared to r, and point a, b in its domain, we can set up the functions f1 and f2. And if both of these are differentiable at the points a and b respectively, then we have 2 partial derivatives, d1 of f and d2 of f, at a, b. Now, if both these partial derivatives exist, we simply say the function is partially differentiable at a, b. And as the name indicates, we haven't yet got to the concept of differentiable. But partial differentiation, from a geometrical point of view, is quite interesting. Let's go back to our example of x squared plus y squared. You see, to get the partial derivatives, we sliced in these 2 planes. The partial derivatives gave us the slopes of 2 lines, one in each plane, and these lines are tangent to the surface at this point. These 2 lines themselves define a plane, and it's this one. Let me show it. We call it the formal tangent plane to the surface at that point, and we use the word formal to indicate that the plane really depends just on these 2 lines. And for any point on the plane not on these 2 lines, but we don't know really how that point relates to the surface. Well, we want the algebra for this particular formal tangent plane, but before we can do that, we need the algebra for any plane.
You may recall that the equation of a line through a point AB with slope m is y minus b equals m times x minus a. Analogously, the equation of a plane through the point ABC is z minus c equals m1 times x minus a plus m2 times y minus b. Now, what are these numbers m1 and m2? Look at what happens when we put y equals b into the equation. We get an equation in x and z, and it's just that of a line with slope m1. Similarly, when we put x equals a, we get an equation in y and z. It's also that of a line, but with slope m2.
Well, that's just what we need for our formal tangent plane. So here's the equation for a plane through the points A, B, and C. Now, to get our formal tangent plane, we took a slice parallel to the x-axis through the point AB. And on this, y equals b. So that disappears, and we're left with the equation of a line with slope m1. But this is the first line that defines the formal tangent plane, and we know that its slope is given by the first partial derivative of the function at the point AB. Similarly, to get the second line, we took a slice parallel to the y-axis. There, x is equal to a. That disappears. We have a line, slope m2, the second line defining the formal tangent plane, which has slope given by the second partial derivative of f at AB. And now, for our particular formal tangent plane, x squared plus y squared example, we have this. See, through the point 1, 2, and 5 on the surface, and we worked out the first partial derivative to be 2 and the second partial derivative to be 4. We'll come back to this equation later, but first let's look at a second example of a function from r squared to r. This is the function. It's represented by the surface, which is mostly this plane, a vertical distance 1 above the xy plane. But over the y-axis, the surface consists of this tilted line going through this point here. In other words, the surface is that of a function which maps 0y to y plus 1, the points on this line, and it maps every other point just to 1. Now this surface has a formal tangent plane at this point because the function is partially differentiable at the origin. See, if we take a slice in the x direction, we get a horizontal line which is differentiable, and its tangent is also a horizontal line. If we slice in the y direction, we get a line of slope 1. Again, obviously differentiable, and the tangent is again just this line. So the formal tangent plane that's defined by these two lines is this one. Now for this function, we can see that the formal tangent plane really does depend on the x and y directions and not on the shape of the surface. Have a look at this function, which has this surface. Again, it's mainly this horizontal plane at distance 1 above the xy plane, and above a line at 45 degrees to the x-axis, the surface is this tilted line. You can see that the shape of the surface is exactly the same as that of our second example. It also has a formal tangent plane. When we slice in the x and y directions, we get horizontal tangents. So these define a formal tangent plane which is just this horizontal plane. Same shapes, but very different formal tangent plane. Well, perhaps we should go on now from looking at slices in just the x and y direction to looking at slices in a general direction, and we'll go back to our first example, that of x squared plus y squared.
So here's our general slice, here's the cross-section, it's a parabola, and again we're going to think of it as the graph of a function from R to R. But what function? Well, we're going to have to look in a little bit more detail at this line here. It's the intersection of this slice with the horizontal plane, and we're going to assume that it makes an angle alpha with the x direction. Suppose we assign the value 0 to the point 1, 2. And suppose we assign the general value t to the point at distance t along the line. Simple trigonometry tells us that it's the point whose coordinates are 1 plus t cos alpha and 2 plus t sine alpha. The value of the function at this point is 5 plus 2t times cos alpha plus 4t times sine alpha plus t squared. And it enables us to define a function, f alpha, from R to R. It's a function in the variable t, mapping it to this value. The point 1, 2 we're interested in corresponds to the value t equals 0. We can differentiate this function and find the value of its derivative when t equals 0. Right, so here it is. It's the slope of this tangent line. And we call it the directional derivative in the direction alpha, and we write it like this. If the directional derivative exists for each value of alpha, we say the function is directionally differentiable. And in fact, we've seen that our function x squared plus y squared is directionally differentiable at this particular point, and the value of the directional derivatives is given by this formula. Now, if a function is directionally differentiable, we've got a whole range of tangent lines through the point. And the obvious question to ask is whether all these tangent lines lie in some sort of plane. Well, if they do, it'll have to be the formal tangent plane. And the reason's simple. You see, when alpha equals 0, we're taking a slice parallel to the x-axis, so we get the first partial derivative. And when alpha equals pi by 2, we're taking a slice parallel to the y-axis, so we get the second partial derivative. Okay, let's look at this in a little bit more detail. Let's look and see whether all our tangent lines do lie in the formal tangent plane. If they do, then the directional derivative is given by the slope of the line that's the intersection of the formal tangent plane with this slice in the direction alpha. Let's check and see if that's true. For the points on the slice, we know what the x and y coordinates of a general point are, in terms of t and alpha. The first coordinate x is given by 1 plus t cos alpha. The second coordinate y is 2 plus t sine alpha. So x minus 1 equals t cos alpha, and y minus 2 equals t sine alpha. The formal tangent plane is z minus 5 equals twice x minus 1 plus 4 times y minus 2. So the equation for the intersection is z minus 5 equals 2 cos alpha plus 4 sine alpha all times t. That's a line with slope 2 cos alpha plus 4 sine alpha. And that's exactly what we wanted, because this is the formula for the directional derivative that we found earlier. So all the tangent lines do lie in the formal tangent plane, at least in this case.
Well, what about our second function with this surface and this sloping formal tangent plane? Well, the function is directionally differentiable at the origin. Take any slice, we get a line which is differentiable and is its own tangent. But if we take a general slice like this, the tangent, the horizontal one, lies in this horizontal plane and not the formal tangent plane. In fact, the only two tangents that lie in the formal tangent plane are the ones that define it. So the two examples we've looked at, both are directionally differentiable at the point in question, but for the first, all the tangents lay in the formal tangent plane, while in the second, only two did. Well, that's as far as we're going to take constructing R to R functions. We're now going to look at the definition of differentiability of a function from R2 to R, and the definition is a direct generalization of that for a function from R to R. And this is the definition. Just like the R to R case, you see it comes in two parts. Well, let's see how we get this first bit. In the R to R case, we looked at certain lines, and here we're going to look at planes. Now remember, this is the equation of a plane through the point A, B, and C. So if the plane goes through a point on the surface, C is replaced by f of AB. And for a general point on the surface, Z is replaced by f of xy. Now for each xy, we want a value for M1 and M2. So on the right here, we have functions f and g of x and y. And just as in the R to R case, at the point AB, we want the values of the function f and g to be such that f and g are continuous at AB. Now, if we can find two functions f and g such that 1 and 2 hold, then we say the function f is differentiable at the point AB, and its derivative is given by this pair of numbers, the values of f and g at AB. From this definition, we get three results. The first says that if a function is differentiable at a point AB, then it's continuous there. That's quite easy to see from this first equation. We consider these as functions of x and y, they're continuous at AB. We're given that f and g are continuous at AB. This is just a constant. So by the sum and product rule, we have that f is continuous at AB. Now, the second result says that if f is differentiable at AB, then it's partially differentiable at AB. Again, that's quite easy to see from this first equation. If we put y equal to b in this first equation, this disappears. And now this, with y equal to b, is the value of our f1 function at x. This is the value of the f1 function at a. Capital F with y equal to b is continuous at a by this condition. So we see that capital F with y equal to b is nothing more than the chord slope function for our function f1. So the function is partially differentiable at ab. The first partial derivative exists, and in fact is the value of capital F at ab. Now similarly we could put x equal to a in this equation and arrive at the second partial derivative existing and being equal to the value of g at ab. The third result we're interested in says that if a function f is differentiable at ab, then it's directionally differentiable there, and all the tangents lie in one plane. And the proof of this is in the text. We want to go back now to our first example, x squared plus y squared, and see if this function is differentiable at 1, 2.
Let's look at the left-hand side of part 1 of the definition. Here, f of xy equals x squared plus y squared. And now, since the point we're interested in is 1, 2, f of ab is just 1 squared plus 2 squared. We now need to rearrange this to find candidates for our functions f and g. And we do this by taking out factors x minus 1 and y minus 2 like this. So, candidates for f and g are the functions x plus 1 and y plus 2. We know these are continuous everywhere, and certainly at the point 1, 2, where they have values 2 and 4.
Well, what about our second example? Well, this function is not differentiable at the origin. You can say that immediately because all the tangents do not lie in the one formal tangent plane. If it was going to be differentiable there, they'd have to by our third result. This function also shows that the converse of our first two results are not true. See, here's a function that's continuous at this point, but it's not differentiable there. And it also has partial derivatives at this point, but again, it's not differentiable there. But even the third result, even the converse of the third result is not true. If you look at this function, and it's made up, its surface is made up of this plane, except for the points on this circle. At the origin, the surface is still down here on the plane, but for all other points on the circle, the surface is raised a distance 1 above the xy plane. Well, this function is directionally differentiable at the origin, because if we take any slice through the origin, we get a function that looks like this, and you can see that that is differentiable at the origin, and the directional tangent lies in the horizontal plane. All the tangents lie in the xy plane. But this function is not differentiable at the origin because it's not even continuous there. And that breaks our first result. So you see that differentiation is really much stronger than the special types of derivatives we considered at the start of the program. The line of development we followed is from partially differentiable functions to directionally differentiable ones, to ones whose directional tangents all lay in one plane, and finally to differentiable functions. And in each case, we've been narrowing down the number of functions that satisfy each of these in turn.